Yes, now when it comes to types of heterocyclics, we have aromatic and non-aromatic heterocyclics. Now, what are the differences between these two? We need to know the differences. For an heterocyclic to be aromatic, one, it should obey Hűckle's criteria or Hűckle's rule. Hűckle's rules. What are the rules? One, it should be cyclic and planar. What do we mean by planarity? It should lie on the plane. For example, if this is a plane, this piece of paper, if it's a plane, this marker lies on the plane. It rotates on the plane. But if I make it penetrate through this piece of paper, this part will be this side and this part will be the other side. So it is lying perpendicular to the plane. Even if it's like this, like it penetrates, it won't be on the plane. Here it's on the plane, rotating on the plane, but here it is perpendicular to the plane. So that's the planarity. The heterocyclic should be cyclic and planar. You can say it is flat. That is one criteria. Another one, every heteroatom, every atom of the ring, every atom of the ring must have any hybridized, unhybridized. It is unhybridized p orbital. So we shall see this. We shall see this. Another rule or criteria is that the heterocyclic should have 4n plus 2 pi electrons. So to have 4n plus 2 pi number of electrons. So its pi electrons should be gotten by this formula. So this n, the n is an integer. So it can be 0, can be 1, 2, 3, etc. So when n is 0, if n is 0, meaning that it will be 4 times 0 plus 2. So n can be 2. If it's 1, it will be 4 times 1 plus 2. So n is 6. Then 4 times 2 plus 2, n can be 10. Then next will be 14. Meaning that we have no 8. We have no 4 here. And we have no 8. And we have no 12. So we are skipping some even numbers. Therefore, if you have an heterocyclic compound satisfying these two criteria, but its number of pi electrons, is either 4 or 8 or 12, it cannot be gotten by this formula. It means that it's not aromatic. It's an heterocyclic, but it is non-aromatic. So we shall see the examples. For example, for aromatic, we have this. It is an aromatic heterocyclic. Then we also have this one. It's also an aromatic heterocyclic. So we want to prove, are they aromatic heterocyclics? Are they satisfying this Hűckle's rule or the criteria? 1. It is cyclic. For example, this one, it is cyclic. That's 1. That is 1. It is cyclic. Is it planar? How can we test whether it's planar or non-planar? So for planarity, it should be sp2 hybridized. It should be either sp2 or sp1, you get, but it should not go beyond sp2. Shouldn't be sp3. So how can we test this? So here, that's why I say that a student should be well conversant with hybridization and molecular geometry. But let's try to explain. Now, nitrogen, its atomic number is 7. So, mean that its electron configuration is 1s2, 2s2, 2p3. This is its electronic configuration. Mean that if you want to draw hybridization at the ground state, it will be like this. We have 1s, then we shall also have 2s having 2 electrons, then 2p. Okay, let's do this. This is 2s, then we also have 2p. And remember, 2p has 3 suborbitals having 1, 1, 1. Then at excited state, say excitation, we are having the 1s2. Then the 2s2, this one, electron will go to the 2p3. So to come, we form this. Then these two unpaired electrons will be like this. So this is at the excitation state. Now, when it comes to hybridization, this N, we shall have 1s2. Then for nitrogen, we shall form this. We shall form these electrons, they participate in resonance. The lone pairs will participate in resonance. So that's one of the criteria. They donate electrons. They donate, provide electrons for resonance. So it can bring its lone pairs of electrons, but sometimes we shall find, like some rings, the heteroatom provides only 1 electrons for resonance. So this is heteroatom. The heteroatom provides electrons for resonance. For example, we have this pyridine. This pyridine, nitrogen provides only 1 electron for resonance. But this one provides 2 electrons. And if you take this formula, you can see that it really provides 2 electrons for resonance. So mean that if these ones they participate in resonance, they are unhybridized. So we shall have this and unhybridized lone pair of electron. And this is 2p, this is 2s, this is 1s. So this is still 2p, 2s, 1s, this is 1s. This is now hybrid, it is sp. It is sp. And it is sp2 because we have 1s and 2 p's, so it is sp2. This is p. This is 2p, and it is unhybridized. These are hybridized. These are hybridized. So please check for the videos of hybridization and molecular geometry. These are hybridized, meaning that it satisfies one rule, is sp2. So mean that nitrogen will have these electrons lying on the plane to provide these electrons for the bonds to lie on the plane, like this and hydrogen. Now this unhybridized electron will lie perpendicular to the plane. To be perpendicular doesn't affect the geometry of these ones. So this one will lie to the plane, then the other one will be just perpendicular to the plane. So it is planar. This one provides a planar structure, and these carbons also sp2 hybridized. So we have double bonds. All the carbons are sp2 hybridized. So it is cyclic, it is planar. Then every atom of a ring must have unhybridized p orbital. So we have unhybridized p orbital for N. And if you do the hybridization for carbon, we shall have also a p orbital, which is unhybridized. And when it comes to the number of electrons, we have 1 pi electron here. Another one is here, those are 2. We have 3, 4, and these 2 which are donated, these ones, so making them 6. So satisfies this rule. We have 6. So it obeys Hűckle's rule. All the 3 criteria. Furan. This is furan. Furan. Don't worry about the names. We shall find the nomenclature. We shall talk about nomenclature. This is furan, and this is pyrrole. Pyrrole. So we shall talk about nomenclature. Don't worry about the names. So aromatic heterocyclics, they obey Hűckle's rule. And due to resonance, these electrons, they are moving. They are not localized. They are moving in the ring. So this one increases stability. Resonance increases stability. So they are more stable than non-aromatic. We are going to see non-aromatic. They are more stable. And this stability makes them less reactive. They are less reactive compared to the non-aromatic, because electrons are not available for reactivity. They keep on moving. Yeah, they are rotating, so they are not available for nucleophilic reaction or for electrophilic attack. So they are less reactive compared to non-aromatic. So let's talk about the non-aromatic heterocyclics. But before going to non-aromatic, let's talk more about resonance. About resonance, for example, this structure, you have N and these 5 carbon atoms. If this one is having an hybridized p orbital, we shall have an hybridized electron. And also this carbon is having an hybridized electron. And this one is having this one is having this one is also, they are all having an hybridized p orbital, meaning that this electron can form a bond with this one and this one. Then this one forms with this one, or this, like up and down. This is the other side of the plane. This is above the plane. Also, this one can form a bond like this. So these two can form bonds. These ones can form bond, and these ones can form bonds. So we shall have a donut-shaped structure. Up, we shall have electron cloud, and down. So mean that we shall have N like this, with this one forming a bond, this one a bond, and this one a bond. But again, it can change. Instead of this one forming a bond with this one, it can change and forms a bond with this one, and also downwards. Then this one forms upwards and downwards. Then this one forms with this one, like that. So we draw the structure like this. It has changed now. Bond is here, here, and here. Not here, here, and here, but here, here, and here. So that's the resonance we are talking about. The electrons keep on rotating. They keep on rotating. So this is what we call resonance. They are not localized on the atom. So they are not available for reactivity. So they are less reactive compared to non-heterocyclic. So let's go to non-aromatic. Let's go to non-aromatic heterocyclics. Yes, for non-aromatic heterocyclics, non-aromatic, these ones. One, for them, they don't obey. They do not obey Hűckle's rule or criteria. And they are the electrons are localized. Electrons are localized on atoms of the ring. So the electrons are localized. So they are not in resonance. They are not in resonance. Mean that they are available. The electrons are available in case of lone pairs. In case they are lone pairs, for example, this structure. This is tetrahydrofuran. Tetrahydrofuran. So don't worry about the names. We shall find nomenclature. This structure, we shall have lone pairs on oxygen. And these ones, they don't participate in resonance. There is no resonance in this structure. These carbon atoms, they are sp3 hybridized. They are sp3. Also, oxygen is sp3 hybridized. So we have no resonance, meaning that these lone pairs, they are available for reaction. So they are available for reactivity. Or this heteroatom is nucleophile. It is mononucleophile. And mean that they are available as bases. They can act as bases. These non-aromatic. They are more basic. When we talk about bases, basic or basicity, they are more basic, mean that they can attract protons. They can attract protons because they are available. Electrons are available. So they are more basic than aromatic. And another thing, we said most of them, the atoms, they are sp3 hybridized. And their structure, if they are sp3 hybridized, means that they are tetrahedral. They have tetrahedral structures. So we shall have this structure. We have an atom having 4 bonds in tetrahedral shape. So having, this is X, Y, Z, maybe P, this shape. So they cannot lie in the plane. They are out of the plane. The moment an atom is having this structure, it is out of the plane. So it cannot lie on the plane. So, and they have no special stability. No special stability. Like for aromatic, because you said these ones, since they have resonance, they are more stable. So these ones, they have no special stability. So no resonance. Since there is no resonance, no special stability. Another example, this structure. This is pyridine. 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 It is non-aromatic, but pyridine is aromatic. This is pyridine, and for it is aromatic because its electron, one of the electron, is participating in resonance. One electron is unhybridized. It is in p orbital, unhybridized p orbital, and it is having lone pairs. But these lone pairs, they are outside the ring. We shall explain this more as we are heading here at comparisons between the structure, electron density, distribution, electron reactivity. So we are going to explain more these ones. So this is pyridine and this is pyridine. This is non-aromatic, but this is aromatic because it has resonance and atoms, they lie on the plane. Also they have pi, it has 4n plus 2, pi number of electrons. Now this one does not obey Hűckle's rule, but this one obeys Hűckle's rule. So we shall explain more and more as we are going through that topic. So this is non-aromatic heterocyclics. These non-aromatic, they behave like the non-cyclic, they are non-cyclic analogs. They behave like they are non-cyclic analogs. For example, this one behaves like the straight chain amine. It behaves like straight chain amine, the 5-membered carbon amine. This one, because its electrons are available for reactivity, like for 5-membered aliphatic amine. By this one, its electrons, one of the electrons participates in resonance. This one, furan, behaves like the ether, 5-membered ether. It has no special stability. But the moment you put double bonds, it changes from tetrahydrofuran to furan. And if you put double bonds, means that this one is is aromatic. Is aromatic. We shall see. So from here, I'll pose a question. Is this structure aromatic or non-aromatic? Is it aromatic? Is it aromatic? So try to check whether it satisfies the aqueous rule and what is its name. So, but for the name, you should watch the video up to nomenclature. So at the end of the topic, you should be able to name this heterocyclic. For the aromaticity, at least for now, you can check whether it satisfies the aqueous criteria or aqueous rule. Please put the answers in the comment section and see whether you really follow the discussion. Here we have a hydrogen. We have hydrogen here. So oxygen, nitrogen with a hydrogen, and we have double bonds. So let's go to comparisons.